lesson 1.2.2, electron configuration. So from here, we're transitioning from the classic Bohr model of an atom to the quantum mechanical model of the atom, something we discussed previously. The topic we're looking at today specifically is from our Glencoe textbook, and this is Chapter 5, Section 3. The first thing we're going to look at is atomic orbital diagrams. All right, so on the vertical axis here, we have it labeled energy. Now, the lowest energy level possible, as we kind of discussed previously, is the 1s energy level. The next highest energy level is the 2s energy level, followed by the 2p energy level. After 2p is 3s. After 3s, we have 3p. After 3p, we have 4s. After 4s, we have the 3d energy level before we have the 4p. This is an atomic orbital diagram as we see on page 135 of the Glencoe textbook. Now, unlike the Bohr diagram, which if you recall, we had rings, or n equals 1, or n equals 2, and we had electrons that occupied regions of space. That's essentially what we're doing right now, except instead of putting electrons in these individual rings, which correspond to the primary quantum number, the 1s, the 2s, the 3s, and the 4s, the 1s and the 2s in our Bohr diagrams, we have further subdivided it into sub-levels, the p-type orbits, the d-type orbits, as we described in the previous exercise. Now, the first rule that we're going to look at is the Aufbau Principle. The Aufbau Principle states that each electron occupies the lowest energy orbit possible. So that would mean that the lowest energy possible at the moment is 1s. Electrons can't start at any high energy level. They would have to start at the lowest energy level possible. Kind of like when you pour water into a glass, the water starts at the bottom of the glass and then fills all the way up. There's a certain gravitational attraction to the bottom of the glass. In the same way, there is an electrostatic attraction of electrons towards the nucleus, and 1s is the closest to the nucleus. Let's draw a diagram for the element carbon. Carbon has the atomic number of 6. This means that its number of protons is equal to 6, and its number of electrons is equal to 6. When we describe the atomic orbital diagram, or the arrangement of electrons around a carbon atom, we explain it using atomic orbital diagrams. We have 6 electrons to describe. So let's apply the Aufbau principle. Our first electron of the 6 electrons we have to describe will occupy the lowest energy state. Next is the Polyexclusion principle. This states that each electron in an atom has an associated spin, similar to the way a top spins on its axis. So much like a spinning top, the electron is able to spin in only one of 2 directions. So an arrow pointing up represents an electron spinning in one direction, whereas an arrow pointing down represents an electron spinning in the other direction. The Polyexclusion principle states that a maximum of 2 electrons may occupy a single atomic orbital, but only if they have opposing spin. This is an atomic orbital, this little position here, this slot, this opening. So our second electron will occupy the same atomic orbital, but have an opposing spin. Let's continue. We have 2 electrons of 6 drawn. We have 4 electrons drawn. Perfect. 2 left. This is where Hund's rule comes in. says the fact that negatively charged electrons repel each other has an important impact on the distributions of electrons in equal energy orbits. So for example, in the 2p, there are 3 atomic orbitals, each of equal energy. Hund's rule states that single electrons with the same spin must occupy each of these equal energy levels before they start to pair up with opposing spin. This would be similar to if you and your friends went on vacation. If there were 3 beds, you'd probably each take your own separate bed or your own separate room before you started doubling up. This would be the atomic orbital diagram of carbon. If we were going to write the shorthand electron configuration of carbon, we could describe it as 1s2 to describe our first energy level. There are 2 electrons in the 1s. The next highest energy level is 2s. There are 2 electrons. And then the final energy level that has electrons in it is the 2p, and it holds 2 electrons as well. 1, 2. Question many students will ask is, how am I supposed to remember the order of energy levels? 3d fills after 4s. What's going on? All right. Let's give this a try here together. All right, figure 519 on page 138 of our textbook describes that this sublevel diagram shows the order in which orbitals are usually filled. Well, let's go over how to use this diagram. You'll recall that in the primary quantum number 1, there's only one sublevel possible, and that's the s sublevel. There is no 1p, there is no 1d, only 1s. When we move further out from the nucleus in our quantum mechanical model, we can have the 2s orbit and a 2p orbit, but that's the total number of sublevels that can be found under the second primary quantum number. When we move into the third and the fourth, additional orbits become available. A question you might have is there a 6f? Yeah, but no element in the universe uses it, not in the ground state. Is there a 7d? Yeah, but no element in the known universe uses it. So for our intents and purposes, we list all of the orbits that are possible, just as we see in figure 519. The lowest energy level is 1s, followed by 2s, followed by 2p and 3s, followed by 3p and 4s. Then it's 3d, 4p, 5s, and I think you're beginning to see the pattern. Let's finish up. Sorry, I ran out of space there. All right, so that's the order of energy levels. So if we were to ask to write the ground state electron configuration for, say, bromine, let's do an example. First thing we need is the atomic number of bromine. We look it up on a periodic table, and I believe we get 35. This means the total number of electrons is equal to 35. We have 35 electrons to describe for bromine. So it's like the great Canadian musician Drake says, we start at the bottom, 1s. Our s orbit can hold a maximum of 2 electrons. So we have 2 electrons described, only 33 to go. Let's follow the order from lowest energy to highest energy and complete this electron configuration. 2, 4, 10, 12, 18, 20, 30, 35 electrons, 4p5. This is our electron configuration. Now, one thing I want you to identify is that on the periodic table, bromine is found in the 4th period. It's also found in the p block. we're divided into 4 blocks, the S, the P, the D, and the F blocks on our periodic table. Bromine is found in the P block. And within that P block, in the 4th row, if we count from left to right, it is the 5th element. This means that the final highest energy level of our electron configuration should give us the home address on the periodic table of that element, which again I find super fascinating. When Dmitry Mendeleev set up his periodic table well over 100 years ago, nearly 150 years ago at this point, it predates the nucleus. It predates our understanding of the atom. But when he arranged that periodic table, I find it fascinating that he also arranged it according to the quantum mechanical characteristics of each element. Amazing. And this is connected to the periodicity of the element, because Mendeleev, all he knew was elements that had similar properties and increasing mass. That's how we group them. And this is where the quantum mechanical model really begins to become accepted, that it begins to explain all these fantastic phenomena that we've been observing up to this point. All right, the last thing I would want to talk to you guys about is the noble gas shorthand configuration. The first instance of the highest energy level, in this case 4, 4 is the biggest number. It describes the beginning of. That means that all of these elements correspond to the core. These are the filled inner shell electrons. One thing you might notice is with 2, 4, 10, 12, 18 electrons in this core, what element on the periodic table has 18 electrons? It's got 3 filled shells. You know what it is? It's the noble gas argon. With its 18 electrons, we pick up, reading left to right in our periodic table, 4s2, 3d10, 4p5. And that's the noble gas shorthand configuration. You recall the atomic orbital diagram of a carbon atom. This is something we looked at previously. Now, hybridization involves, this is our valence shell here, involves the hybridizing or mixing of the valence electrons into 4 equal energy bonding orbits. So in order for an element to form a chemical bond, its valence shells have to hybridize. So in this case, let's show that hybridization. So we have 1 s orbital and we have 3 2p orbitals. 1, 2, 3, 4. When these mix together, we have 1 s and 3 p's. So we call this sp3 hybridization. Once these 4 orbitals have mixed together and hybridized to form 4 equal energy orbits, we apply those same rules, Hund's rule, and what we end up with are 4 single electrons. Now, when we draw out the dot diagram of carbon, we draw the symbol for carbon, and we try to represent 4 distinct regions. Typically, it's above, below, to the left, and to the right. These are imaginary spaces, but for the moment I'm sketching them out with my highlighter. I hope it kind of shows up on the screen. Now you'll recall we have 4 valence electrons in carbon. In hybridized bonding orbits we have 4 spaces in which we can fit electrons. When we draw those dots, 1, 2, 3, 4, we have our Lewis dot diagram for carbon. It's worth noting that lone electrons in our diagram is equal to what's called bond capacity. So carbon has 4 lone electrons, so it can form 4 bonds. A quick shortcut on your periodic table is, if you look at carbon, carbon is in group 4A on our periodic table. it has 4 valence electrons. Let's draw nitrogen. Nitrogen is in group 5A. How many valence electrons will nitrogen have? If you said 5, because it's in group 5, you're correct. Now, something you're going to notice here, this is what's called a non-bonding pair. So single electrons will form bonds. Carbon will form 4 bonds because it has 4 single electrons in its dot structure. Nitrogen has 3 single electrons and a non-bonding pair. So this means that nitrogen will form 3 bonds because it only has 3 lone electrons. Its non-bonding pair, as the name suggests, doesn't form bonds. All right, good luck, take care, see you all next time.